considered. Anything we thought might be important to water, or sorry, overall quality. And final gravity, for example, we couldn't measure that as ourselves, but we were able to get that information from the brewery. It's measured in degrees Plato, and it has to do with the density of the beer. It's more dense than water.
So there are a couple of water quality parameters to take into account when you're looking at the overall brewing process, mainly pH, dissolved oxygen, hardness, mineral content, and chloride levels. And these all have the most effect on the final taste of the beer. So the pH is the measure of the acidity or alkalinity of a solution, which is on a logarithmic scale, where 7 is neutral and lower values are more acidic and higher values are more alkaline. And the pH is really important in the mash or in the beer because it affects processes from enzyme function to hop extraction to yeast vitality. So it's really important to have a water source with a stable pH before the brewing process. So it saves you time and money by not having to manipulate the mash pH with other calcium and magnesium salts or other acids or stabilizers. So the dissolved oxygen is the amount of oxygen that is present in the water. It's measured in milligrams per liter. And dissolved oxygen is very important in the brewing process because you have to have enough oxygen to feed the aerobic breathing process of the yeast. So too little dissolved oxygen can result in low or sticky fermentation, off flavors, poor yeast crop, and low alcohol production. And too much dissolved oxygen results in rapid fermentation, which results in excessive yeast growth and beer losses. And it can also result in a higher alcohol production, which can produce a fruity tasting beer, which is undesirable in certain brews. So the hardness is the measure of the amount of calcium and magnesium salts in the water. So the more calcium and magnesium in the water, the harder the water is going to be. So the water hardness mainly affects the mash pH. It either raises it or lowers it, which can ultimately affect the overall efficiency of the mash. And so again, for the mineral content, we mainly focused on the iron because the Star Hill and consumers and us, we noticed that there was almost a metallic taste to some of the brews over the different seasons. So we mainly thought that was due to the iron content because the iron salts can have negative actions at concentrations above 0.2 milligrams per liter during wort production, and high levels can prevent complete saccharification, which is the process of breaking down complex carbohydrates into simple sugars. And it can also result in hazy worts and hampers yeast activity and cause the metallic taste in the final product. So the chlorides, they're very weakly basic and they're readily neutralized, and it actually accentuates bitterness and increases stability of any solution, and it actually improves the clarity of the beer. And the salt taste of the chloride generally enhances the beer flavor and the palatefulness of it. And chlorine is often used in city water supplies as to sanitize, and it can also reach high concentrations with the use of bleach as the brewing sanitizer, but not to our knowledge. Star Hill, to our knowledge, does not use bleach in any of their brewing, the sanitizing steps. So heavily chlorinated water will result in almost a medicinal taste or more chlorine-like flavors that are very undesirable in a final brew. So if the water coming into the brewery is very heavily chlorinated, you can reduce those levels by putting in a carbon filter, which Star Hill actually does.
So out of our little motley crew, I'm the number cruncher data type person. I did a lot of the data analysis. And a part of the data analysis that really tends to get put behind the scenes is the actual data assimilation. But because it was so extensive in our project, we really wanted to bring it to the forefront. So we had data from our own water sampling, from the fermentation logs, from the NCDC website, and then the raw output from the ion chromatography and atomic absorption processes. And in order to be able to analyze all this data, we had to put it all into some kind of format we could actually look at. So the first step was to combine all the data from the individual water sampling events and the laboratory processes into a single Excel workbook. And then we transformed the fermentation log data first into an Excel spreadsheet and then into a comma delimited file, which, for those of you who don't know, a comma delimited file is basically just a string of numbers and words separated only by commas. If you opened it in a basic text editor like Notepad, it would just be a single string. And then we prepared the comma delimited file with weather data and beer data for analysis in R. And that's the reason why we use the comma delimited files, because that's how R understands data. And R is a statistical analysis and graphing software. It's really great. You put in what you want it to do, and it does it pretty much. So our approach to analyzing the data was to first analyze the water quality data in Excel, and then determine what was statistically significant data and include that in our comma delimited list. And then use R to statistically analyze the data and generate graphs using R. This is basically an overview of the slides that are to come, because the following slides are mostly graphs. One of the other crucial steps was to figure out what was a statistically wet day versus a dry day. So when we plotted a histogram of our precipitation and how frequently a certain level of precipitation occurred, we got this histogram, and it looked to be approximately exponential decay. So using our knowledge of that, we found the mean to be about 0.05 inches. So we determined that to be our threshold with any day. So if a day was preceded by more than 0.05 inches of precipitation, it was considered wet. If it was preceded by less than 0.05 inches of precipitation, it was considered dry. So this is some of the analysis we did in Excel. And basically what we were looking for here was any kind of pairing and trending of the data. The dissolved oxygen doesn't really show us much, but one thing that was particularly interesting about the pH samples was that after we see this bump in the samples at the reservoir, we see a similar bump a short time later in the water that we saw at the brewery. And the delay is obviously because you're not going to use the water in the reservoir in the brewery that day. So we think that this could indicate the delay, the potential length of the delay between the reservoir effects and the brewery effects. And here we have the hardness of the water samples and the chloride content of the water samples over time. Again, we were just looking for anything, looking for any kind of pattern that indicated a relationship. Most of what we drew from this, though, is that the data varies a lot, and that happens with data that you take straight from nature. And here we have the nitrate content and the sulfate content of the water. And one thing that's particularly interesting about the sulfate content is you can see that the reservoir samples are down here, whereas the brewery samples are all the way up here. And what this indicates is that during the water processing at the water handling facility in Crozet, they add sulfates to it for some kind of cleaning or for some kind of taste and quality improvement. And one thing that I found particularly interesting about the nitrate content of the water over time is that it gradually goes up, like there's an upwards relationship. And since we were looking for trends over the seasons, we think that if you were to continue taking this data throughout spring, summer, and then the following fall and winter, you may see it trend upwards through the spring and summer, and then downwards again through the fall and winter, indicating some kind of relationship with the quality as it changes throughout the seasons. Here's where we get into some of the really cool stuff that we got to do in R. These are just some box plots that we have, showing the final pH of the beer following wet or dry conditions, and the pH z-scores of the beer following wet or dry conditions. And z-scores are a quantitative statistic showing how far our value deviated from the expected mean value. And so what we can see here is that the pH varied very little based on dry or wet conditions, as did the z-score, so not really anything statistically significant. But then when we moved on to look at the final gravity of the beer and the gravity z-scores of the beer, like James said, the gravity is the density of the beer as compared to water. We noticed that it varies widely after a dry day or a wet day, as does the z-score. And when we saw this, we thought, well, we can see it with our eyes, it looks statistically significant, but to verify that, we wanted to do a 2-sample t-test. So we did that using R, and our alpha value was 0.05. So if our p-value for our 2-sample t-test was less than 0.05, we know that we have to reject the null hypothesis, which is that the difference between the means is not statistically significant. And because our p-value was 0.01586, we knew we had to reject the null hypothesis, which means that the alternative hypothesis is true, that the difference between the means is not 0 and thus is statistically significant. And this is where we got into some of the more fun analysis that we got to do in R, where instead of just looking at things that we knew we were going to look at, we started to play around with the data and look for something that would really show us what we wanted to see. Here we have a graph showing the precipitation as these vertical black bars here, and the red is the gravity z-scores over time. And what this is showing us is a general downward trend of the gravity z-scores, indicating that the gravity could also be changing over the seasons, which is potentially interesting as we were looking for changes over the seasons. And here we have the pH z-scores against the precipitation over time. And although these don't show any particular trend, one interesting aspect is that after a major precipitation event like these two here, the pH z-score drops dramatically. So we think this could be indicative of a need for Star Hill to really mitigate any changes in quality that could be occurring after major precipitation events.
So basically we have two main conclusions. First, that there seems to be a noticeable delay in major precipitation events and the observable changes